So, what did we do? 1, 2, 3, 4, 5, 6. And then total 1, 2, 4, 6. Volts, current, resistance, and power. Although the truth is, we will probably be able to come to a conclusion fairly readily. So it looks like you got a couple of powers down here. 0.85 watts, and then 0.558 watts. Here we had 12 ohms, 22 ohms, 130 milliamps, and 596. So let's change that to 13.0 amps and 0.59697 amps. Then up here, we've got 7.28 volts and 34.17 volts. I think that's all the information available to us. So, what's kind of the first general rule? Just do any math you can do, right? Well, maybe even before you do any math you can do, since stuff is kind of scattered around, is it possible for any values that are up there that were given to be plugged into other places? So in other words, if I had two parallel resistors and the voltage drop across one would be the voltage drop across the other, or the current going through one in series is the same as the current. That doesn't get you anything. Oh, that's his pile, right?
Yeah.
But you can put it there if you want, but it's his pile, not mine. Yeah. Okay, so having said that, can any of the values be used elsewhere? Generally, the resistive values cannot be. They're unique to each spot, and the power values will be unique to each spot. But the amount of current going through one part of the circuit could be going through other parts of the circuit, and the voltage drop across one branch of a parallel component could be the same as across others. So if I look at resistor 4, the current going across resistor 4, is that the same as the current going anywhere else? No, it's a part of the current going everywhere else. How about the current going across resistor 3? Or going through current resistor 3? Isn't that also the same as the current going through 2 and 5? So I should be able to take your value 130 or 0.13 amps and plug that right into here without doing, and where was it, 5? Without doing any other math. Okay. Now let's see. Does the voltage drop do much of anything for us? I can't. Voltage drop across 6 is going to be unique to 6 and nothing else. The voltage drop across 5 is going to be only part of the voltage drop across 4, so that doesn't help us. We can't plug those values in anywhere. Okay? So now we're at a point where we can do the math in a couple of places. So basically, for 2, 3, 4, and 5, we can start doing some math, right? Now, another option that might make things even more simple is we have said the amount of current going through 3 equals the amount of current going through 2, right? And we know the amount of current that's going through 4 because that was given. So therefore, all of the current that's going through 2 and 4 must be coming from 1 and going into 6, right? So the simplest first level of math would be to add those 2 branches of current together. Okay, so if I take 59 and add 13 to it, that gets me to what, 69, 72, 69? 0.72697, and I can plug that into not only into 6, but I can plug it into 1, and I can plug it into T, right? Okay, so what did I say? 0.72697 amps. 72697 amps and 0.72697 amps there. Well, now I don't need to do any more analysis, do I? I mean, for all of the different loads, I now have 2 ingredients. So I can calculate power and resistance for each one. Once I've done that, I can then back extract to voltage total. Or if I've got all the resistances, I could do the circuit analysis and get R sub T. Or since I've got all the powers, that's a straight adding problem. I can add all the powers up. In fact, I should kind of do all of those and then make sure the totals add up, and that would be my cross check, right? Okay, so from this point on, the problem should be pretty straightforward, right? Ohm's law. We don't necessarily need to do anymore. Okay. We'll find out. Who else is locked in? I had Vargas came wandering in late. Rodriguez came wandering in late. Anyone else? Okay, so new problems. Ramping it up, 7 resistors. I don't know, we'll see if you guys can handle it. 7 resistors and a few tricks. You know, we're heading towards Halloween. We got to start getting practice on the tricks, right? Okay. Calculator. All righty. Okay, so I had that we were just sort of in the middle of talking about components and stuff, so we'll just keep trudging along that path. Clean this up permanent. Okay.
Pin numbering systems.
We're still in wiring. Why are we doing this? Just go to look at that one. Or am I wrong?
I think you're wrong. What I have last connector pin numbering systems.
Okay, maybe it's slipped down. So we hadn't talked it with.
I think that was probably about the last one.
So I got it in there. Okay, I got like this one off back. And I've gotten to. Thought I had already talked about some of this.
Yep, tools.
We talked a little bit about the tools and then bent pins. Different types of, or not so much the types of connectors, but separating the two. A little bit final on the tools. So I guess we're just getting done with connectors, right?
Yeah, I think that's the last page.
That's the last one right there. Okay. My thing just slipped off and slipped down some. Okay. So there are within the 40V13 Bravo, one Bravo, there is several charts that specify wiring requirements based upon allowable voltage drop and the length of the wire versus the amount of current being carried through it. And then from that chart, you determine where you end up on it, and then the next largest size wire, using the American wire gauge, is the wire you want to use. However, there are multiple scenarios. The wire could be freestanding all by itself, it could be in a big bundle, it could be in a conduit, or it could be in a very hot environment. So you may have to calculate or calibrate for temperature. So within those charts, you are going to have to sort of play with them a little bit. The advisory circuit actually gives you an example and walks you through an example. I could try to describe that, but the truth is the advisory circuit does a better job of than anything I would try to describe. So I highly recommend you follow your way through that on 4313, just so you're kind of clear about how to use those charts. Okay, identification. It used to be all wires were white. In fact, back in really the early days, and I still, one of my wife's rentals still has a house that was built before wiring existed. So the wiring is not internal to the wall. It's actually external to the wall on porcelain things and porcelain little pegs, and it's fabric wrapped wire. Still actually in pretty good shape, surprisingly. But In the world of AC, they just said there's black, there's white, there's green. You don't even know much more. Don't really care because they're all kind of going to do the same thing. They did play with some colors here and there. In the world of automotive, they immediately went to all kinds of colors as soon as they came up with reasonable plastic insulation, which is usually polychloride or polyvinyl chloride. Polyvinyl chloride is not acceptable for use in an airplane because above certain temperatures, polyvinyl chloride either melts and sags off or actually catches on fire and becomes part of the flame source. So we, for many, many years in aviation, the type of insulations that, Tefl or other higher end polymer insulations that could handle the temperature and didn't typically burn, it was very easy. It was fairly easy to make them in a white, but to make them in any other color, the dye would affect how the material behaved, particularly with respect to combustion. Now that's changed in the last 10 or 15 years where you can buy mil-spec colored wires. They cost more. Okay, it's more per foot, in some cases by a substantial amount, versus buying yourself a decent labeling machine that not only will label the wire, but if it's, if it's a sophisticated one, you can program it to label the wire as it's streaming it out and cutting it off and stripping the ends for you. Well, that's a much better way to go. So the end result is you still see white wires being used a lot, but there, again, there is some color coding with a limited amount of color. Just because it's color coded doesn't mean it doesn't need to be labeled. And labeling is required in aviation wiring. Now, make no mistake, that cool little machine right there with a spool on it ain't cheap. Okay, I have no idea, but probably in the neighborhood of 20,000, something or more. Okay, it's going to be an expensive little machine. So I don't know why they do this. They should be spanked for doing it, for even considering doing it. But every once in a while, the wire will change in a connector. So instead of being a 1 Alpha Bravo Charlie, it becomes a 1 or a 2 Alpha Yankee Mike or some other designator as it goes into and comes out of the connector. That's a little annoying. Another thing that can occur is and this happens for one of two reasons. Somewhere in the middle of the wiring harness, you might see a wire that's just soldered together, stuck together, soldered, and fully insulated, wrapped up in and bundled in the harness. That can occur where you have an instance that two harnesses come together and they really only interface on that one wire. So they'll leave it strung out and that part of the harness very loosely wrapped, bolted all in the airplane. Once it's all in the airplane, those two wires are brought together, soldered, insulated, and then everything is triced up appropriately. So you might see that. The other place it can occur is, and it's a little less of a problem when you're using white wire, all white wire, and you have a labeling machine right there. Okay, because you can make as much wire as you need. But in the world of color coding, and I've seen this probably half a dozen times in automobile wiring harnesses, where VW runs out of purple green wire. Darn. They don't stop building cars just because they ran out of purple green wire. They just go, darn, grab a different color, throw it on the machine and keep on going. Somebody makes a note, as of RPM serial number, that note may or may not make it back to the tech writers. Okay. And, of course, that whole chain of process to the point that it actually gets to you. So there you are with a connector and a wire heading out that's purple green, but you go to the other end of the harness, and no matter where you go on that harness, that purple green wire doesn't come out. Like, where did it go? And nothing you read says anything about that particular wire. Now you've got some problems. And unfortunately, sometimes the only way to find it is to start splitting harnesses. Sometimes the identification process will include data about wire size. So in other words, if it uses 2 at the third character, it means it's a number 2, or some other cross reference that you don't necessarily know what it is, but it might be cross referenced in the initial index as it describes some things about in the manual that's describing how the wiring system manual works. So sometimes the actual part number or identification number of the wire gives you information above and beyond just what wire it is. Okay. And of course, the little machine you're seeing, looks like it's probably, I would call it a laser jet. What it's probably doing is spraying a small cloud of ink, of toner, at the side of the wire while a laser scribes and the toner sticks. Might be inkjet, but I can't imagine ink would be very permanent. Whereas toner being heated into the wire, probably quite a bit more permanent. I will also tell you that many times I've seen that labeling fade away and disappear. Is it UV? Is it chemical exposure? Is it just bad ink to get from the get-go? I don't know, but okay. So here's a couple of examples of wiring charts, and you'll note that they've got several different things. So in this particular one, we're giving you different curves. One curve is for continuous rating, continuous power, wire is in a conduit or bundle. The number 2 is continuous rating, but wire is in free air, and it's a single wire. So it allows you to do a little bit higher or a little bit smaller wires for the same amount of current. And then curve 3, which lets you go even further out, is intermittent duty. And of course, do they tell you what the intermittent duty is? Maximum of 2 minutes. So whatever that amperage value is, no more than 2 minutes. So these different curves allow for some different possibilities. This particular one, instead of having the curves, what they do is they have a temperature correction chart. Okay, so whatever the typical temperature is going to be, you then correct for it. But essentially what you're going to do is you're going to say, you're going to start out with what's the basic distance of the run. And in this particular example, they're saying, it's like about 52 or 53. They're then going to run out to whatever the appropriate amperage is. So in this case, it doesn't look like it's right at 15. It looks like it was at 14. They're then going to drop down to the appropriate wire size based on whatever curve they hit. They're going to come down to here, and note it's slightly past the 10 gauge.
What do you mean 50? Is that like the
The length of it is 50 feet
50 feet.
for 12 volts, or for, in this case, 28 volts.
Okay.
25 feet, and that's to achieve no more than, and this actually clipped the bottom of it, but to achieve no more than a 5% voltage drop. So that's the chart's based on. So at 50 feet, 24 volts, whatever it was, 52 feet, I'm going to go out to whatever the approximate current rating was. And again, I think I've lost it here. I keep seeing 15, but 15 is here. So it actually looks like 18 or so. Then we're going to come down to here. We cannot use 10 because 10 is too light of a wire. We'd have to go up to an 8 gauge. We'd actually go to a 9 gauge, but they don't make it. So we've got to go to an 8 gauge.
So the smaller the number, the thicker the...
Right. American wire gauge works bigger number is smaller wire. And unfortunately, what that means is when you get to 1, you're kind of out of luck. You can't go any smaller. Well, so what they then did is they said there's 0. Then they went there's double 0,
Where's
and
the
triple 0, and quadruple 0.
where's the number for what kind of wire it is? Like,
That's these numbers here.
right.
That's the gauge of the wires right here. So you've gone out to here, voltage or length out to, based on the correct voltage chart, length out to current
Well-
drop down or up, either way.
I'm sorry, I meant to say like, is it copper or aluminum or how do you know?
There's only really about 4 applications I know where they use aluminum wire.
Okay, so
So it's all gonna be copper wire for these. Doesn't say it, but,
yeah, that's
so
okay.
essentially, and depending on what, if you can get away with just using that chart, you would then use it. And then of course the bottom end of the curves are going to be the maximum amount of current that you can run through any single segment of a wire. Okay, so if I was down here, it may well be that I go off the bottom here based on what's happening, in which case I'm gonna have to go either to less current for much heavier wire. Okay. Now the way these charts will work is interactive with each other. A value I come up with here, I may then need to take over to the second chart based on, let's say I'm running in the engine compartment. I know it's going to be really hot in there. So this one's going to include, I'm going to do the same thing in that one, but now I'm working off of a correction formula for higher temperature. And that formula is located down on the bottom of the chart. Okay, and again, I'm not going to throw any of these at you, but know you will see some of these in potentially in the written exam, or excuse me, the practical exam come test time. So I would strongly recommend practice the example in 4313.1 Bravo. They narratively walk you all the way through it. And then change some of the values and practice it again.
Do you know where in the FARS it has labeling requirements? I was looking in 0.5, didn't see it.
I'll send you all the way back. Where would you find labeling requirements for parts, airplanes, systems in general?
23.
Part. Come on, nobody remembers what part applies to, that tells you how to properly label any part?
What I'm just,
Defines terms like FAA, PMA,
I was wanting to
defines in number, registration numbers.
I wanted to find what the requirements were for marking.
Not 22? No. Send all of you back to general. The whole lot of you. Part 45. Okay, proper identification of systems, subsystems, and entire airplanes. Now, a couple of caveats that make our life a lot easier. One of them is the ATA, or Airline Transport Association, along with several others, have created some reasonable standards for wiring diagrams and wiring labeling, as well as the mil-spec that tends to get used. Not universal, but those do tend to get used. The other thing that's important to you guys is, what's the name of this little advisory circular? AC 43, what's its name?
Practices,
Huh?
practices, something.
Practices and things and stuff. 40, huh? Acceptable practices. Okay, it doesn't mean what you should do, but it's acceptable, right? Now, most of the time, if you're going to be doing wiring, you're either, you got a bad wire and you're just doing a repair. You'll do it through the AirFrame manual, and you'll essentially replace what was there, okay, presuming it was right in the first place. The other reason is if you're doing some kind of an alteration. And predominantly, there's really only two ways to do electrical alterations. Major electrical alterations coming from a radio shop, or excuse me, coming from like installing a bunch of Garmin's, a new radio stack, a whole bunch of stuff like that. Those guys typically are only going to sell their products to radio shops anyways, because they don't want anybody else installing them. And so the radio shop is going to do all of their work under their repair station certificate, and they're going to have all of this documentation laid out appropriately. In fact, they may have it in terms of production documentation directly from Garmin or Bendix King, etc. However, for a lot of that other equipment, like it's you know, a fuel flow gauge or an engine monitor or some other thing like that, the manufacturer of those types of electrical devices, they don't really want to have to rely on the radio repair station certificate. They want you guys out there, the much bigger number of mechanics out there, doing these installs because they'll be selling their product more. So it behooves them to go out and get an STC for their product to be installed on a bunch of different airplanes, right? The STC should include all of this data, and it will be approved data versus acceptable data. Now, they might have copied everything from here, but you don't care. All you care is it'll say, umped up wire from here to there for that length of wire, use this size of wire, use this size circuit breaker, route it this way. You're just, this is golden, this is great. You've got a whole bunch of approved data. If you don't do that, you're going to be resorting to this and possibly a field approval of your 337, either based upon this or DAR, DER work. There's a whole bunch more paperwork for you. So, fortunately, in the world of electrical installations where rewiring occurs, these guys do a reasonably good job. Now, some of the older STCs that I've had the joy to play with, they just say refer to these charts. Okay? Because it used to be 4313 had some really good information in it that you could rely on. And so it was fairly straightforward to do that. Nowadays, my general sense is the FAA has become a lot more prescriptive, in part because of 4313 doesn't do as good a job. But I think the bigger problem is the FAA themselves have become less competent, so they don't actually really understand what it's doing here, what's really being displayed or being said here. So they don't trust it as much. So they're more inclined to say, well, if you want to do that, you got to go get an STC and take it through engineering. Because then they can say, well, we have our designated engineer and we trust them because we designated them. Ain't it grand, right? Yeah, it's scary. Okay, so we typically mount wires. You need to mount them. There are some guidances and some rules. Manufacturers often will be slightly tighter than the rules. So, but there'll be some spacing requirements. I think no more than 2 feet, if I remember correctly. But typically we'll use what's called an ADEL clamp, which is also known as a frustrating little piece of stuff that you're trying to hold several of them together, get a bolt fed through there when they're trying to spring open, and the appropriate number of washers in some weird little bitty hole. Okay, you don't have, this is before the skin's riveted on. Now the skin's riveted on, and you're reaching up underneath here to get to that little ADEL clamp to do. Yeah, they're evil little things. They do come in a variety of different sizes, all the way up to very large. Typically, well, above a certain value, they actually only go in 1/4 inch increments, and I forget what that is. I think it's 3 inches or might be 2 inches, but somewhere in there, they jump up a 1/4 inch each time. Below that, it's 1/8 inch increments. The double attaching is actually kind of useful. They make their aircraft spruce makes a set of vice grip pliers with these 2 little clamps welded onto it. that you take and run an all the way through, and then 2 clamps come down, clamp it down, and hold it all in place. Pull the awl out, put your hardware in there, get it started, then release it. And they also make them where they have their own little latch. So you bring it down and put the little latch in, then the bolt goes right through. They, of course, cost twice as much to have that extra little latch stamped in there.
They make hinged ones now too.
Huh?
They make hinged
They make
ones.
hinged ones as well. They cost 4 times as much. Okay. Always want a little bit of sag between hard points. You know, you think about how long an airplane can be. Boeing 747, by the time you go from the nose all the way to the tail or all the way out one of the wings, and it goes from minus 39 degrees over the North Pole down to Phoenix Sky Harbor where it's plus 122 degrees, it's going to be an inch longer, an inch or more longer, wider, once it warms up and gets good and warm. It's going to grow quite a bit. So the wires need to be able to respond to that. Copper doesn't have the greatest amount of thermal expansion. Aluminum has great thermal expansion. So a little bit of sag point just to allow it to shrink and expand, and or a service loop, which would be even more. The FAA does allow you to zip tie. They are not meant to be structural. They're not good for high heat environments. If you use them in high heat environments, they will sort of change kind of a funky color, and eventually they get to the point where you can go snap and they shatter. Don't ask me how I know.
They have high heat supplies now.
They do have high heat. Yeah, and so
Yeah, we've never had an issue with them.
I've actually used them for a while, and I think they're fine. It's just this is sort of one of those areas that A&N Hardware, you could say it's A&N Hardware, right? Mil specs, this, that, and the other thing. Zip ties,
They have a mil spec number.
they do, but yeah. So, and I use them all the time. They're wonderful. Any wiring harness where you're going to need to get in and out of it once in a while, zip ties are the easy way to go. Okay, a wiring harness that's pretty much going to be there for the life of the aircraft. You're never going to do much to it. Lacing is a much better way to go for a couple of reasons. It does a much cleaner job in my mind. It doesn't have those little bloody things that stick out and rip the skin off like the zip ties do. And it you know, it just looks cleaner. That said, to have to unlace to add a new wire can be quite a pain. They do make little wire shoes that just a small little sort of pointy piece of plastic that you can slide up underneath the lacing to lift it up enough to get another wire under it. You just keep, so if the lacing isn't too overly tight, you can actually I can just work my way along here, slide a wire up underneath, slide a wire, feed a bunch through, and just keep working it all the way along however I need to route it. So it's possible to do. So lacing, like I said, it's also lighter, quite a bit less material. You're basically using the same thing that we use to rib stitch, and it doesn't weigh nearly as much as the zip ties do. Like I said, and again, nothing wrong with zip ties. There are many, many, many great uses for them. For many years, the FAA actually they were like, we're not going to say anything. They've now included it in their in several different places. Spaghetti, which is sort of a pre-made semi-conduit, spiral wrap, split tube, etc. My problem with that is, again, unless you can come up with some mil-spec, which I think there actually is some mil-spec stuff, not cheap. Most of this stuff is polyvinyl chloride. Polyvinyl chloride does not do heat well. Okay, it's around 220, 230 degrees. It's up getting really soft. How many places in an airplane are at 230 degrees? Not many, until they're on fire. Okay, once the thing catches on fire, Now substances like polyvinyl chloride, not only do they readily burn, but they release all kinds of nasty toxic substances. So if that's going to be in an area that doesn't normally get very hot, it's probably an occupied area. So now all the rules around fire protection come into play. So these are things you all kind of got to consider. However, it may have been done. Spiral wrap, spaghetti, these things are all very, very easily used. Another one they've got is it's a woven tubular fabric that works pretty well. Again, there somewhere I've acquired a roll of it that's actually is high temp nylon. It's good up to about 350 degrees. Some of this stuff, it actually works reasonably well to put it on and then put a piece of heat shrink on the ends to terminate it. Makes a nice clean installation. Okay. And there's also varying degrees of heat shrink. That some can handle temperature well. Some of the better quality heat shrink, not only does it shrink and clamp things down, but it bonds itself to the wire and seals. They also have heat shrink connectors now that they have for a while that have the solder inside the heat shrink. So you just take the two wires and stick them in there, heat the whole thing up, the solder melts, fuses the wires together, shrink comes down, collapses around the wire, and seals it. It's as if the wire was never broken in the first place. However, it has been broken, and even using that really cool, nifty, thrifty heat shrink, automatic shrinking thing, you're only allowed one break in the wire. A number of things we can do. We can put harness shields or conduits. Standoffs are very common. The only caveat here is every time you do that, you're adding a reasonable amount of weight, right? That's a little bitty, probably a little bitty steel clamp or set of clamps there. There's some A&H hardware. Not a good idea to take your wiring harness and wrap it 3 times around the exhaust pipe. Any other fluid lines of any kind, probably don't want it too near, you know, or certainly below. You don't want it too near oxygen lines as well. I think to do the job well, you need to make nice concentric, symmetric turns and routing so that it looks relatively sanitary, and something that's been damaged or in other ways mechanically affected, it becomes obvious. I've got 9 wires that play out real nicely, and one of them looks all kind of funky and doesn't look right. Well, that, you know, it's because the connector broke or came loose. Now it's dangling, but it stands out. It's real obvious to you, to the eye. Your eye finds it quickly. That said, sometimes you don't have a choice. It's just going to be a rat's nest. There's so much stuff put in so densely that, and there's a lot of wires in the front of an airplane. Typically, if there's any relative motion, a small amount of relative motion, it's a good idea to put a 90 degree. If it's a rigid wire like an EGT thermocouple or any other heavy wire, you might actually want to put a couple of loops in it. Okay? Or if there's a fair amount of relative motion, you might want to do a couple of loops. The amount of motion that occurs oftentimes is only a millimeter or so. Not much, or maybe a little bit of rocking, etc. It's not much. But over the life of the engine or life of the installation, that's a lot of movements. Okay, millions of movements. So if that's happening over a longer stretch, it's going to it's going to last a lot longer. Now that said, how long should it last? Well, thermocouple probes, especially exhaust gas ones, tend to get fried in the exhaust gases, fairly readily, 500 to 1,000 hours, something like that. So, but on the other end of the coin, the CHT ones, they're much lower temperature. They tend to last for life of the engine at least. You definitely don't want to make a route a wiring harness so that it looks like a very convenient step or handhold. Um, and that's also true even if it's in a conduit. You do not want the conduit to be regularly stepped on, swung from, cargo attached to, and dangled from, that kind of thing. There are some instances where you're going to get either wire needs to be routed near something that it could affect magnetically, or just for the convenience of keeping the pair together. It's not uncommon to see two wires twisted together so that the current going out and its magnetic field is the opposite of the current coming back, and they're all intertwined so the two cancel each other. And greatly reduces the amount of magnetic field coming off of that wire headed in and out. I've seen a number of cases where, if I take a piece of shielded wire, single conductor shielded wire, I actually have two conductors, right? I've got an inner conductor and then the shielding to bring everything back. Seen a lot of instances where power goes out and ground comes back. That's the way it was done. I sort of frown on that. Shielding should be used for shielding. Okay. The problem is you don't know how much current that shielding is really designed for, do you? You can calculate how much current the center conductor was designed for because they gave you a value for that. They gave you 22 gauge or 24 gauge. But they don't tell you what the gauge is of the shielding surrounding it. And so it may be a voltage drop coming back. Now, I do concur with the general practice of not running grounds back through the airframe. Again, there are many cases where it's hard not to, but I just have seen so many ground loop problems over the years that grounding the chassis is not always the best way to go. Does add some more weight though. All right, buses. I don't know if it's two S's or one S. Depends on Merriam-Webster or Funk and Wagnall or whoever you look it up. The idea of a bus is power distribution. It's no different than what we've got going here. In here, there's a big fat wires come into here, and then there's these big metal plates that come down either side. There's three of them. Okay, so big fat wires come into here to the three circuit breakers. They then attach to these three big metal bars that come down through here. Those are buses. Then each one of these clip onto each one of those metal bars, depending on whether or not they're gang. These will clip onto two different metal bars. So what happens is each hole is a different metal bar. Okay, so that'll be bar A, bar B, bar C. This will be staggered off one. This will be B, B, C, back to A, all the way down. So that I then load share all the way across. So really, in truth, that's three different buses all combined into one box. Because in this case, the electricity we're using is three-phase AC. And in cases where we need two phases or all three phases, we gang the circuit breaker together so that if any one side decides to go, it's going to kick the rest of it out. Okay? So good for power distribution, ground distribution, gives you a very good mechanical means to connect stuff together. So rather than a freestanding crimp, you've got solid eyelets coming together at the same point. It's very possible to have a bus that's actually, it's really more of a connector plate. Each set of screw holes, paired screw holes, are independent of each other. And where you want to gang them together, they have a little device that hops over the fence and gangs them all together. Okay, the FAA has sort of said in 4313, let's keep it down to 4. That way, if the screw breaks, comes loose, I've only lost 4 things. The other thing they have discovered is if you mix all these metals up and then run electricity through them, they might corrode. Well, that's kind of logical, right? And depending on the different metals you mix together. I will tell you, stainless steel is sort of remarkable. For being stainless and not wanting to corrode, you get it near get it near copper, bad things happen. For the copper, you get near aluminum, really bad things happen to aluminum. So it's very, very bad for other metals. So, and I think I may have said this earlier, but we typically see buses arranged in groupings for various functional operation. Now this is very true in much larger airplanes. So, but it's common to have, this is a fairly small primary bus, than a fairly large avionics bus. And the idea there is, in use, the pilot typically is going to pre-flight the airplane, go around, do a few things. They're going to get in the airplane, fiddle around in the cockpit for a little bit, and they're going to turn the master and the avionics bus on. Okay, tune in the frequencies they need, and then set up their IFR clearances or takeoff clearances, whatever they need. They're going to set it all up. They're then going to shut the avionics bus back off, fiddle around, getting the engine started, other checklists, do a whole bunch of other stuff. Then, once they're ready to go, they'll kick the avionics bus back on, call up ground, and get the clearance to start taxiing and do whatever they do. So, the advantage of that is if I've got one switch in here that lets me actually shut that off, I can then shut off a bunch of devices during start phase or other operational phases. Okay. It's also very, very common, particularly on larger airplanes and military airplanes, to have redundant buses. For, I've got, bus 1 and 2 and an A and B on each one, and any one can be channeled to help, to back up for the other. So if I do get a short and I have to shut one down, I can route around it. Another strategy for bus design, which I don't tend to see this too much in aviation, but we do it in ground-based stuff all the time, called the ring bus. So for example, all the buildings and structure in this college, all the power comes from a big ring. That way, if somebody nails one corner of the ring, you can isolate that out and you have the other pathway to route power out to all the different buildings. That creates a level of redundancy. And of course, obviously the bus, both current carrying capacity, so the physical size of the screws and the plates, etc., to handle the current, and as well how well it's insulated from whatever it's attached to, so that if it has reasonably high voltage, the voltage isn't going to leak and go someplace it's not supposed to go. So they typically are made from copper or a plate of copper. In this case, somebody put a bunch of probably thread studs from the backside and then mounted that onto a plastic plate. And they even made a nice little cover over it. Here, whoever's building this, they did a very nice job of keeping everything nice and clean and concentric. What they did is they came in, first off, all power distribution comes in on big white leads and everything goes out on red. They then came in and they said, all right, well, we're going to take and have a big lead come into here, or maybe it's this one coming into here, and we're going to apply power to this copper strip, which is attached to each one of the circuit breakers. It's going to jump across to here, each one of these circuit breakers, and then note it doesn't go anywhere else. Then there's another one that's just this bus here, and another one that's that. So this actually has 3 independent buses in there, and they've used copper strips to just directly interconnect all of those circuit breakers together. Okay. That's pretty clean installation. Now, one of the things we don't know is what's the voltage drop for that copper strapping. As long as its cross-sectional area is bigger than the wires, the total cross-sectional area of the wires going to it, for that short distance, you probably don't have much voltage drop. Okay. So I think I've already said this. The one downside of a common bus is that if any one part of it shorts, if it's this side of the circuit breakers, your only option is to shut everything off. Okay, so you may have to shut all your avionics down, which maybe I want a comm avionics bus and a nav avionics bus, so that if one goes, I still got the other, right? So most often we try to design the circuit around, I've got a battery, I'm gonna have a pretty short lead coming out of the battery to wherever it grounds. And that's true regardless of wherever it's mounted. I'm gonna have another lead coming out of the positive side, and if the battery's way in the back of the airplane or forward of the firewall or wherever, it's gonna have to go quite a ways before it gets up to where we use all that electricity. So oftentimes they'll put the master relay right next to the battery box. They may even put a starter relay there too. So the only really big fat cable that comes forward is the starter cable, but a much smaller, like a double A, or, you know, or an 8, or maybe even a 6, runs everything else. Okay, so those two relays may sit right near the battery box. That's actually a good thing. That way, if that big positive lead, it's as short as possible. If it shorts and you can't, that's the one. If it shorts between the battery output and the master switch, you can't shut it off. So if you keep that really, really short, very, very short thing, then the potential for it to get shorted is very little. So so from there, I'm going to run all the way forward to wherever my circuit protection is. I'll probably have a bus distributing out to the circuit protection, and then from there, and it's a fairly short run from the bus to the circuit protection. From there, it then goes all the way out to all the other different devices: fuel pumps, strobe lights, nav lights, instruments, avionics bus. So yeah, it's fairly typical to ground. If the battery's in the back, it's very typical to ground it to the airframe. Oh well, what they do. I don't recommend grounding, bringing the ground back through the chassis of the airplane. It's a viable thing to do where RF isn't an issue. But in an airplane, man, you're up there collecting all kinds of static electricity. The ability to have your nav equipment work and your communication equipment to work is pretty important, particularly in really bad weather. And yeah, running electricity through the chassis of the airframe can sort of interfere with that in some cases. So what I have found is, particularly in audio circuits, I've had to completely isolate the audio circuit from any ground plane. But in doing that, I then got the noise to go away. And I mean the complete audio circuit. Even the ground for the intercom, grounds for the radio, all had their own common bus. And then coming out of that, that lead from that bus then went right down and attached to the bolt that the main ground cable for the battery went to. So it has straight a shot as possible to the negative side of the battery. If you have a lot of really weird stuff going on, open the door and the wipers come on kind of stuff, oftentimes it's a ground plane issue. Something in the ground side. So what happens is electricity goes, well, I'm used to going that way to get back, but I can't, so I'm gonna go back through this circuit this way.
Is that what's called a ground loop, or
Yeah,
can you explain a ground loop?
so for example, BMW 329s, they had an electronic ignition circuit. And the power that went to the electronic ignition circuit was fairly fancy, and it was a simple little thing, but the grounding path for it came back to the main fuse panel. There was a problem in this big multi-jack thing that went to the bottom of the fuse panel, and one of the connectors for the relay for the fuel pump, ignition unit, and everything else went into this, and it wouldn't connect that well. Okay, instead of going in the hole like that, it would go like this. And so just after it got out of warranty, it would start becoming a high resistance. Well, the ignition unit would figure out a way to, instead of going to ground, since it lost that, it went through the coil of the relay back onto the positive side of the circuit, across over to the headlight relay, and back through the headlight relay coil to ground, which would cause enough energy to activate the headlight relay. Once the headlights would come on, that would create enough of a power drop in this already weakened circuit that the ignition would shut off. So the customer's complaint was, I was driving along and the high beams came on and the engine died. Huh? They're not anything to do with each other. Well, the one thing they had to do with each other was the ground. Okay, and the ground was a weak link because of the way this connector went together. I had to stare at that schematic for a long, long time to figure out how ground was finding it. It kept looking like it was finding its way through the headlight. It wasn't finding its way through the headlight. It was finding its way through the coil, activation coil of the high beam relay. However, when they did that, the high beam relay came on enough to where now system voltage, instead of being at 13.68, was at 13.2 or whatever. So all those little voltage drops dropped the igniter unit to below the threshold. So it just said, I can't do it anymore.
Well, weren't most aircrafts, general aviation aircrafts, weren't they grounded through the frame?
Very commonly they are. I mean, it is what it is. Again, if you start having really weird problems like that, but the other thing is it doesn't necessarily have to go through an electronic component. It can go through a mechanical component. Okay? You can have a one-shot ground loop. Customer complains, I got in, started it, and it was really, really weak, and the speedometer blew a puff of smoke out and then it stopped working. Well, in that particular model vehicle, the entire suspension was rubber mounted. The engine was rubber mounted. There was a ground strap. When the ground strap broke, the only possible connection between the battery connected to the chassis and the entire drivetrain was the speedometer cable and the two parking brake cables. Okay, well, it would melt both parking brake cables and lock them solid, which made it a real bear for the tow truck if the brake was on. They'd have to just, brute drag the car up onto the, and of course that little coil spring in the speedometer, when it saw 300 amps, poof, hence a little bit of smoke coming out. Again, it's a ground plane problem.
Thank you.
The other thing of it is, the other place a ground plane problem will show up is if you've got components blowing out quickly. Light bulb only lasts for 3 or 4 months. Or the starter, I forget why, I was in the Toyota dealer at one point doing something, I forget what, but one of the technicians comes in and says, man, I don't know, there's got to be something else wrong. We put 9 different starters in this car and keep having to put new starters in. And I'm like going, oh, it was a warranty thing, because that's how I got the warranty thing done. the service manager is standing there, and I'm like, sounds like you have a training issue. He's like, what do you mean? He didn't know that I worked, you know. I said, well, I can tell you what's wrong with that vehicle. You probably should have said something was wrong after the third starter, not waited till you got up to 9, because those things are probably kind of expensive. He's like, well, can you help me figure out what it is? I said, yeah, can you do the warranty on my new tranny? Because it was, and they were going to do it anyways. But that was a ground plan. So the starter was seeing, instead of seeing 13 volts, the ground strap of the vehicle was partly compromised. Everything else would work fine at their 10 or 15 amps. But when you hit 300 amps across that thing, they were dropping 4 or 5 volts on the starter. Well, what happens to the starter motor? We'll get into this a little bit later. It didn't have enough voltage, so it didn't produce enough counter EMF force. So its resistance never went up high enough. So it was now, even though it had resistance at that plate, joint, it still had way more current. The total fully running loaded current was a lot higher, which was burning it up. Okay, and I know that's counterintuitive. I could never get the mechanic to fully understand how more resistance here would cause the load that's supposed to occur from the starter on the circuit to be so much lower that the total combined resistance ends up being less. But it was fine in the starter. I got a new tranny, so I didn't care. Okay, radios, antenna leads, those little intercoms and microphone circuits, they are really, really sensitive to EMF coming off of anything. So you want to be very careful in isolating those. You want them well shielded. The downside of running a bunch of electricity through the chassis is, where do you ground shielding?
On the back of the radio.
On the back of the radio, if you can. I've seen many, many installations where they don't do that well. And they get noise from the chassis because of it. If you can take it back to the radio, and in fact, some radios, they actually have a special audio ground. Don't attach it to anything else. What is it? One of the Sigtronics intercoms has that, where they have
SPA 400.
and I forget which model, but they have they have the main power ground, but then they have an audio ground.
All Garmin's now have a little stud on the back of each connector where you're supposed to call the shield.
And that stud is the one spot.
Yeah.
Don't put it anywhere else. Yeah. Yeah. And that's the reason for that, is because there's all kinds of noise happening. If that gets connected to ground, the chassis ground, any noise that's happening on that, it's going to be like hooking it up to a big white noise antenna. Okay? And unfortunately, the amount of amperage that particularly exists on a microphone line, audio lines a little bit more, but on a microphone line, the amount of amperage is so small that you don't need a lot of EMF to interfere with it. All right, so let's dive into controllers a little bit, and then we'll take our break. And there's basically two kinds, and they can be used for a variety of purposes. The mechanical kind is usually a human interface device. So all of you with watches, electric watches on, or laptops, all those little buttons are mechanical switches. In most cases, they're a digital device. It's either on or off, open or closed. They have some that actually, they do it an open close per actuation. They can be very, very high current, like the big knife switches. They can be sort of medium current. Here, the distinction between this one and this one, they may both handle the same amount of current. This one, if there's gaseous fumes around, could make your day shorter than you planned. Whereas this one hopefully is sealed, so the spark that occurs isn't going to light anything. This one here, look at 3 different blades. I mean, there's a whole bunch of surface area. This thing is designed to handle some current. Okay, this one here is actually kind of handy. It may or may not be a mechanical relay. It's probably a solid state one. And this tells you everything it does. It's actually 3 individual switches for circuit A, B, and C, 3-phase. So instead of that big circuit breaker in there, or maybe let's say this is sitting in the compressor, the 3-phase compressor. So I've got a relay that comes on, either solid state or otherwise. All I need to do is feed 32 volts, and it looks to me like it's probably solid state because it's saying plus here and minus there. So somehow or another this is polarized. So if I apply 32 volts across here, that's going to connect small a to big A, small b to big B, and small c to big C in a sealed environment. Okay, so what's controlling this? Well, maybe the little pressure gauge and the little computer in the compressor that says, uh-oh, the air pressure dropped, turn the compressor on. All right. So the switches are used in basically 2, and there's another, there are other derivations, but the predominant use of switches are human interface device to turn something on or off, or as a sensor. We often call it a limit switch, but in truth, what it's really doing is position sensing, right? Something comes up and goes whack. Says, okay, we're here. And the switch moves from input to here, goes to state normally closed here to state normally, not normally closed there. Now, this switch, the upside of that particular switch, and this is true of many switches, is I could use all 3 of those leads, or I could just not use that second lead, the one in the middle there, and it becomes single pole, single throw, right? Okay. Right now it's got it's got a couple throws. So limit switch, there, human interface, that's like the big red panic button. Okay, that ain't the easy button, that's the big red panic button. Okay. They can be connected in all kinds of different ways. I was just helping a friend of mine lay out his the torque rod that goes through the length of the airplane from the rear cockpit to the front cockpit to the magneto switch, so that you can operate the magneto switch from both cockpits. Okay, and it's just a big long torque rod with a couple of levers that are then coupled to the magneto switch, but then off, left, right, both, and then start as a separate switch. Okay. Another really sophisticated one that's kind of cool is like the Cessna flap arrangement. So the Cessna flap arrangement, I've got a motor up in there that will drive the flaps out or drive the flaps in if I reverse the leads. Okay. I want the motor to go out a certain amount and stop. I actually want it to go out another certain amount and stop. And then maybe a third certain amount and stop. And then I want it to be able to come back in those increments as well. So what I'm going to do is I'm going to design a switch. It's actually not a switch, it's just a little lever that goes up and down. And I'm going to have a couple of these little limit switches that are designed that if I come up and hit, I'm going to send polarity to the motor in one direction, and if I go down, I'm going to send polarity in the other direction. And those micro switches are going to be bolted to a plate that can move. I'm then going to connect a cable from that plate all the way up to the flaps. So now I take my lever and move it down, and I upset one of those limit switches. It causes the motor to come on going down. So the motor goes down. And that plate starts moving because the cable's moving, and all of a sudden the limit switch comes to an open and the motor stops. Okay, I've now gone 10 degrees. 20 degrees. Come back up. Okay. In this particular case, the lever actually doesn't connect to any switches. All it's doing is upsetting a range of 2 switches for which the whole assembly will move as the flaps move. Yeah, it's a little bit of a Rube Goldberg system. Works pretty well until the cable gets out of adjustment. Then it gets kind of funny. depending on what goes on. So a few, there's looks like a gear door limit switch here, sort of comes up like this and then sits right there. And as that comes up and comes up like this, it closes the limit switch and tells it it's either up or down. Don't really know. This one here actually is the X travel on a mill. So as I engage the drive, it starts going and cutting its way, winding its way along until it gets to there, and then it disconnects. Okay, it shuts the motor down. This picture here is actually a hangar door. Again, this is a big AC, and all this one is doing is saying, okay, you let the door go up too much, it's going to break off if you go any more. We're going to break things, so I'm going to disconnect you. And what it does is, if it's not designed well, it'll disconnect the up. It won't let any more up happen. You can still do the down, but so that's it, you're done on the up. Okay. Now note, that actually looks like a fairly new switch, well adjusted, nice and clean. This one's really nice and clean, well maintained. This one, not so much. The general service requirements for these things is the same as any other mechanical device. What do? I know what you guys do all the time. You get in there, it says lube it up, you just lube it up. No, clean it. Get all the old grunge and grease and dirt and everything else off. Okay, get it nice clean. Do any corrosion prevention or protection that needs to occur. Then properly lubricate it, adjust it, whatever the airframe manufacturer tells you to do. Or possibly engine manufacturer. Nothing too sophisticated there, but these can be a little bit trial and error too. So, you know, it's like jack the aircraft up, retract, retract. So Navion is an example. Navion actually has a switch that says there is no up latch. So if the door, and the switch is actually on the door. So as it comes up, it hits that switch, turns the motor off, and then the gear are hydraulically held up. If that door gets a little bit loose or the switch gets a little bit misadjusted, every once in a while it'll go, and you keep hearing this strange clunk, right? Well, what needs to happen is the aircraft needs to be jacked up, gear swung, switch adjusted, door tightened up, whatever, to fix that. I know that one because I was flying in formation with an Aviation a few years ago, and the gears kept going clunk, clunk, and got under this. Man, your gear keeps hitting me in the head. Fix it. Like, oh, dang it, that's what that clunking is. I'm like, you've been flying this thing for 7 hours with the clunking, you didn't know what the clunking was? Okay. So solid state controllers, we often call them the magic box. In truth, there's not that much magic about them. They're pretty straightforward. They will always have a power and a ground. They will always have inputs, data going in, and they will have data going out. Some kind of output. They activate, they turn something on, they do something. Otherwise, why have it? For the most part, the inputs will be either digital in the form of a switch, or they'll be analog, like a thermal resistor device telling you engine coolant temperature, or the amount of light, hitting it, or manifold absolute pressure, or whatever. So typically outputs are going to be on, off. Occasionally they'll be, so let's say I had like, for example, here the output for these guys is somewhat analog. Okay, I can set the motor to have these lights open in any one of a bunch of different positions. So the control for these, as we've talked a little bit, is typically going to be on the negative side. So we're going to use NPN transistors. this little magic box in here, when you pop the lid off, it's actually not that complicated. Okay? You've got big cooling towers there, the hospital's there, the school's there. The jail is the biggest thing. Okay? I gotta have a big jail. Nah. In all likelihood, this is probably output power filtering. That's the main power supply. Probably computer control and memory is all over here. These guys right here are your big output transistors, right there. Okay, so they're the ones that on, off, on, off. Of course, before you do too much, Ode de fried controller. Okay, if you have Ode de fried controller, at that point, what you're going to do diagnostically is going to change a little bit. Because you're going to be fairly certain that the controller is fried and something outside the controller fried it. Right? Now, more often, and I've done hundreds and hundreds of computer control diagnoses, more often it's either an output device or an input device is giving erroneous data or operating inappropriately. So typically, first two things are power ground. Do I have power ground not out here at the fuse, but all the way back into here? Do I have power and ground actively getting where it should be? And there may be multiple power sources and multiple grounds. In fact, they're off and on. So I'm going to verify all of those. Then I'm going to go through and measure all the inputs. And of course, I need to know what good data is. What should I have in what state? What voltage should I read there? What resistance should I read? Whatever. So that's going to take a little bit of homework. Then from there, go back and look on the outputs. Am I getting? I've got good appropriate data, power and ground, coming in. Is the computer actually telling the outputs to do what they're supposed to do? If they aren't, or if it is and the outputs aren't doing it, it's the output device. If it in fact isn't telling it, then it's something in between. Now inside here, the two things that fail. One is something gets fried, and it's usually that one of those NPN transistors or an inductive spike reducing diode. The other thing, and if that's the case, it's almost always the output device is overloading the circuit. Something's wrong. The other thing that's tend to fail is you tend to get broken solder joints. And that's heat and vibration does that. If that occurs, again, the fix is going to be to replace the unit. You're still going to want to go make sure that none of your devices are overloading the circuit. But you're going to be a little bit more sure that the failure occurred from bad manufacturing, not from something else being broken. Because the two things you want to accomplish is find something that's broken so that you know you're reasonably certain you fixed something. The second thing you want to accomplish is to make sure that what was broken doesn't break again because you didn't fix it entirely. Especially when, you know, that little black box right there, I'm going to guess you're in the neighborhood of anywhere from $500 to $1,500. Okay. So typically replacement is the most common. And I sort of already talked to that. I can tell you when I first started playing with these, the Bosch D subjetronic, what was the word in there? D something jetronic controllers back in the early, really late 60s, early 70s. Every once in a while, one of them would stop working. And you could send it back to Bosch, and for $1,500, they'd overhaul it for you. Man, you could buy a new one for $2,000. That's more than the car's worth almost, right? I kept going, boss, man, let me take the lid off. It's under warranty. No, let me take the lid off. I know there's a fuse in there, boss. Let me take the lid off. Got to be a fuse in there. Well, finally, I forget this case, but it was out of warranty or whatever. Boss said, all right, take the lid off. So sure enough, popped the lid off, half-cent fuse, or a half-amp fuse in there, 20-cent fuse, blown as could be. Popped it out, slapped another one in there, fired it up. Everything's good. I'm driving around the parking lot. Hey, boss, I fixed it. I overhauled. I want my $1,500, boss. driving around having a good time. It wasn't too long, about a year later, what was it? I forget, Volkswagen or BMW North America is calling me up. We're here, you're overhauling those things. Not me, that would make them come out of warranty, and I wouldn't do that. I got pretty good at putting the screw back in and putting the witness paint back on. And, charge the customer $100, you know, and they were happy. They were very happy they didn't have to pay the $1,500. Now, the truth is, I would always sort of tell them, look, the proper fix is to have this thing overhauled. I don't know what all they replace. In all likelihood, it's this little bitty fuse. I can try putting the fuse in there, and if that makes it great, I'm going to presume it just blew out, or you did a jump start or something you're not telling me about. But the warranty is the driveway, you know. Okay. Here's one where I got into a good pissing contest with the manufacturer. They built this really cool, fancy electronic fuel monitoring system. And they had this cool little 15-pin RS-232 connector stuck on the back there, and it's all soldered in place. And they had these cool little gold pins, and well, you can see broken, and completely separated. There's also two more on the other side, broken and completely separated. Well, that's because all of this is mounted into a case. This sticks out the back of the case. There's a big RS-232 connector that sits there that weighs an ounce or so. The wiring harness is somewhat secure, but there's still, you know, engine vibration, that's in there bouncing around. Now, the irony of all of this is the proper chassis mount RS-232 has two pins that come down and connect to the solder, to the board, and it's soldered in place. There are two big pins. The board, you can't see it, it has two big holes with solder pads for that type of connector to be installed in place. This isn't a chassis mount connector. My guess is what happened is the manufacturer got the company isn't actually building those boards. They've subcontracted that out. And somewhere along the line, somebody made a change to those RS-232 connectors. They'll call them up and say, hey, I think somebody's doing you a disservice. You've got these things. They don't. Here's some pictures. That should be able to handle anything. Okay, those are little gold plated copper pins. Cross-sectional area can't be more than 32nd of an inch total. Combine all 9 pins up. I mean, it can't be much. You're sure you're going to go with that? No. You don't know what you're talking. Of course, there's product liability issues. They're never ever going to admit that there's a flaw in their design. So I told the FAA. I warned them. I'll let the FAA know, and if they issue an AD, good luck for you. Now you guys all know how to tell the FAA when you have something like that, right? And it's the same problem with the morning class. You guys all know what a NASA report is, right? A couple of you might know what a NASA report is. So a NASA report is a get out of jail free card. A NASA report is for all airmen, parachute riggers, mechanics, air traffic controllers, pilots, all airmen. It essentially says, in fact, it's not even run by the FAA. It's managed through a different agency, by NASA. The idea was we want to collect information where mistakes are occurring so that we can gather those mistakes and see if there are design weaknesses in whatever system we're talking about and improve them. But nobody's going to tell us that if we're going to throw them in jail. So what they said is they came up with the system. If something happens, either you make a mistake or there's something isn't right, somebody makes a mistake, you fill out a NASA report, and I forget how it works, but you fill it all out. I think you remove your information from it, but the fact that it was attached to that form is your evidence that it was done. It gets mailed in. You do it by certified mail to NASA. It's actually up here in California at what's the Lemoore up there, base up there. And they put the information in. If down the road somebody comes along and says, hey, not from the NASA report, but from radar or from whatever, some other system says, hey, you were naughty, you say, well, I was, but I did a NASA report. They'll say, okay, we're gonna spank your hand and give you the violation, but we're not gonna actually impose it. So if there's a 6-month suspension or something like that, or revocation, we're not gonna do it. That's valid only in instances where it was an honest mistake. If it's truly negligent, malevolent, I wanted to blow the son of a bitch up because he's complete, you know. Then no, it's you don't. The second system, which is actually produced in what's called a service difficulty report, which comes out I think every 2 weeks or every month. You can go online and subscribe to it. It's amazing some of the things that end up in those SDRs. Like mechanic found door falling off because previous mechanic didn't rivet it on. You know, I mean, just stuff that's like, oh my god. But there's a form that's associated with that. That's what I filled out for this. And take no prisoners. Who I talked to at that company, name of the company, their unwillingness to acknowledge or recognize they have a design flaw or possible wrong parts. You betcha. It's just unconscionable on their part. Okay. Now, what was interesting about this was with all those pins that were broken, the only symptom that was happening was every once in a while, it's a fuel totalizer, the amount of fuel it was saying it was getting seemed to slow down a little bit. Well, what was happening was that lead was disconnecting, so the pulses from the transducer wasn't counting all the pulses. So it was using more gas than it was thinking it was using. So there you are flying along, and it's fat, dumb, and happy saying, yeah, you got plenty of gas. Only you don't. That seemed like a dangerous situation to me. Oh yeah, okay, so just a couple more. So if it comes in one of those funny little plastic foil packages, plan on putting the strap on, okay? Now, I don't know about the cool little nurse's hat and the blue uniform. That's kind of cool. I guess if you want to look cool, you can put all that stuff on. Truly, that's not about static protection. It's about contamination, debris and stuff getting into the equipment. The static protection, though, is the blue mat and the little coiled strap that's attached to it and to his wrist, or the example that you see over there. Definitely, you're going to want to use that. Now, this was far more of a problem 20 years ago, 30 years ago. Nowadays, most circuit designers have done a pretty darn good job of making their stuff bulletproof. There's standards around it. For example, the little network plug that you've got in there for hooking up to a network inside of your computer, it's a little modular thing. There's like 7 little wires in there. You may not know this, but if you take a USB plug, you can fairly snugly shove it right in there. Don't ask me how I know. You can nicely just shove it right in there. Of course, the USB plug wasn't designed to go in there. And that outer metal housing is going to lay up against all 7 of those pins and just connect them real nicely to each other. The truth is, nothing will happen. Because the standard for any network output device, any network connector, is you can short anything to anything and it won't damage the computer. Okay? Of course, that's fairly easy to do because data is usually very, very, very low power. Well, it turns out the USB standard is also supposed to be that way. On the USB, you got 4 leads: power, RX, TX, and ground. And the standard is supposed to be any one of them can be shorted across, and it shouldn't damage the computer. And I wouldn't go test that because I don't know that they actually made the power supply and the board and everything to that standard. But there are many cases where we do this, where we create a standard around protection. I do know one of the problems they had, and part of the reason they grounded the space shuttles, was because all the computing systems on the space shuttle were the old TI 8088 processors, very, very slow processors, but you can hit them with a lightning bolt. Okay? And when you're up in space, static electricity is a huge problem. So they're getting zapped all the time. They don't have systems robust enough. They would have to be completely disassemble the aircraft and rebuild it and do all kinds of stuff, as opposed to just come up with a new program, which I'd love to see NASA do it, but it looks like SpaceX is beating them to the punch. Right? Didn't they just hit, I think one of their things, they've now reused it something like 18 times. One of their primary boosters, they've now reused it 18 times. Catch it. They've got their little raft out there with rocket Velcro on it, you know. Okay. Yeah. All right, so they will probably be environmentally controlled. How many of you guys have got a motorcycle with a computer control on it? Okay, where is the controller? Buried down in the middle, right? Okay, it's like the most hidden of everything. Okay, because they're trying to protect it from environmental conditions. They may produce a fair amount of heat. So part of the chassis, the housing, may have all those NPN transistors bolted, glued, stuck to them. All right. And then it gets mounted onto something else that helps keep them cool. For most of these guys, I guess you could say if it's under $1,000 cost, they're usually not field repairable. There are some exceptions. There was a whole while there where in the automotive industry, a bunch of these youngster computer geek guys had figured out how to reprogram them. They'd either pull one of the chips off and put their own program chip in. And they're now busy making a pretty good living on that. Well, the automobile manufacturers have gone full boat, and they've gone over hill and dale to make really, really sophisticated programs that are really hard to reverse engineer to keep these youngsters from doing that to them. So in this particular case, it's like remove the screws, remove the connectors, do some stuff, and out it comes while you're upside down laying on top of the seat, hating life. Of course, what's probably sitting right above that thing is the heater core. And so after a few years, when it finally blows out, it spews coolant, hot coolant all over that puppy. Okay, so let's stop here. How about we come back to Tin Till?